Welcome back. Last week, you guys learned about gravity, Newton's law of gravity, and orbital speed, but this week we are moving into a completely new topic, fluids. This video will summarize a few of the important concepts from the fluids section, which is in chapter 14 in the Physics for Scientists and Engineers textbook. With that being said, let's begin. If you guys have taken a previous physics or chemistry class, you may have learned about the three states of matter: solids, liquids, and gases. This chapter focuses on liquids or fluids. So, what exactly is a fluid? The most basic understanding is that it is a substance that flows. When we deal with fluids, we always want to consider the different types of pressures that exert onto the fluid under different cases. Although I will be elaborating more on this later in greater detail, it is important to recognize that a fluid is incompressible. On a microscopic level, fluid molecules stay together closely, which means that their density remains constant. However, if we consider gas molecules, they can freely move and erratically within a container depending on a pressure or temperature change. Therefore, we can say that gas molecules are compressible since density is a variable and is always changing. And that is based off of PV equals nRT. To break down the idea and organization of fluid mechanics, we can divide the concept into two separate categories: statics and dynamics. Fluid statics focuses on the study of fluids at rest, whereas fluid dynamics focuses on the study of fluids in motion. In this video, we will be focusing on statics. We will want to understand the idea of pressure and talk about hydrostatic pressure specifically, as well as buoyant force. So, pressure is essentially the amount of force exerted onto an object's surface per unit area. The governing equation for pressure is shown here. As you can see from the image, the force vector is always normal to the cross-sectional area. The SI units for pressure is pascals, which is equivalent to 1 Newton per meters squared. Although there are several types of pressure, we will primarily focus on atmospheric and hydrostatic pressure, as they are relevant to fluid statics. Atmospheric pressure is the pressure of air that decreases with height h. Imagine if you have two cases. First, you are on the beach at Santa Monica Pier. At that elevation, you are at sea level, so you can feel a pressure of 1 atmosphere or 100,001,325 pascals. However, let's say instead you were hiking up a 14er in the Colorado Rocky Mountains. At very high altitudes like that, it is more difficult for people to breathe in oxygen. There is less pressure, as we stated, as you go higher in elevation, which pushes oxygen molecules apart in the same volume of air as we breathe in. On the other hand, hydrostatic pressure is the pressure inside any fluid, usually within a container of depth d. The governing equation for hydrostatic pressure is shown here, where P naught is some external pressure and rho GD is an additional component to the hydrostatic pressure. It is important to note that rho GD looks very similar to potential energy, which is equal to mass times gravity times height. To explain hydrostatic pressure in greater detail, we will talk about several examples. First, if we have an open-faced container filled with water, the surface of the water is exposed to the atmosphere. Therefore, P naught must equal to the atmospheric pressure. Second, if the container is completely sealed, then the water inside the container does not experience any external forces, which means that P naught is equal to 0. As a result, hydrostatic pressure is only equal to rho GD. Third, If an elephant or another object is standing on top of a piston, which is part of the container, two things must be considered: the weight of the elephant and the cross-sectional area of the piston. We can assume that the weight is evenly distributed across the entire piston, so pressure P naught equals to force over area. So far, we have only considered pressure P naught. Let us consider an example with rho GD. In this image, we can see that pressure is essentially a gradient. What I mean by gradient is that pressure increases linearly with increasing depth d. Going back to the equation, rho represents the density of the fluid and gravity, and they are both essentially constants. The only variable that is changing is depth d. Here is another example. Imagine if you were in an ocean and you wanted to swim deeper and deeper. As you keep trying to swim deep into the depths of the ocean, the hydrostatic pressure increases because of that depth. This pressure pushes against you and makes the swim very difficult in the end. Next up is buoyancy. The concept of buoyancy stems from Archimedes' principle, which establishes that a fluid exerts a buoyancy force on an object immersed in or floating on the fluid. Therefore, the governing equation for buoyancy force is the product of density of the fluid, the volume of the displaced fluid, and the gravitational constant. To obtain the equation, if we consider the object is submerged or in a fluid inside a container, the object has its own mass and weight. And this is represented by force is equal to mass times gravity. We have also learned that density is equal to mass per unit volume. And this is based off of this equation. If we isolate from mass, we can substitute that into the original force of gravity equation. And this is how we get the buoyant force equation right here. In that manner, we can see that this is the buoyant force equation, and we can move on to covering some examples for it. First, the buoyancy. First, if we are given a container that is only half filled with water, let's say we put a toy boat on the water's surface. Obviously, it will float, and the water will displace a certain amount. The volume of the toy boat is actually submerged inside the water is represented by a yellow rectangle in the image. The height of the water rises by the value h, so the volume of the displaced water is also the yellow rectangle. Second, if a rock is completely submerged in the water, then the water displaces even more compared to the toy boat example. The volume of the entire rock is now represented by the yellow rectangle. As expected, the height of the displaced fluid increased, and for this specific case, the volume of the rock is equal to the volume of the displaced fluid. All right, so we are wrapped up with fluid statics. So if you have any questions or concerns, feel free to comment down below or send us an email. Thank you and take care.